Hey guys, it's Thursday, and of course, we're not going to be doing in-person classes today. And I don't want to keep going forward until we have finished the previous material. So I am purposefully not showing myself. And what I'm going to do is I'm going to share the screen, and I'd like to go to your lecture notes. And we're going to continue and fill in some of the blanks that we had from the last time. Okay, so if you can go here, and I'm gonna just minimize all this stuff so that we can focus on our lecture material. So one of the things we looked at last time was called the Coriolis force. So to remind you, in the northern hemisphere, because of the spin of the Earth, things are going to be shifted to the right in the direction that they're moving. So this shifts the winds, but it also shifts the water. It's the opposite in the southern hemisphere. So things are shifted to the left in the southern hemisphere. So let's go ahead and take a look and see how this affects the wind directions. So this is how everything is set up. So if you can focus in on this drawing that I have right here. So this is the Earth, and it has some approximate latitude. So if you can fill in some of the information. So what we have is, if we go to, let's see. So I'm going to be going to the equator. The equator is going to be a latitude of 0. And if we go to the next latitude, that's going to be 30 degrees north. Going to the next one, of course, we'll have 60 degrees north. And then at the very top, we'll have 90 degrees north. That's the North Pole. So similarly, going down the southern hemisphere, you have your 30 degrees south, your 60 degrees south, and of course, your 90 degrees south as well. Okay, pen's having a hard time writing. Let me switch. Okay, so what we need to look at now is the solar input. So if you can go back to the equator over here, what's happening is we're getting lots of energy coming in from the sun. So I'm going to draw it over on the left-hand side. So we've got lots of energy. This is the solar energy. So the solar energy is coming in, and it's most concentrated at the equator. Less concentrated at the poles, because as this light hits the poles, it's actually covering a larger surface, and it gets more diffuse at the poles because of the curvature of the Earth. So now I'm going to go to the other side. So what happens is this solar energy hits the Earth absorbs that energy, and then what happens is it re-radiates it as heat. So what happens at the equator is that we get air that is rising. I'm getting stuck over here. Air rises towards the equator. Okay, now this is not going to continue forever, but what's going to happen is that it's going to hit the top of the bottom layer of the atmosphere called the troposphere, and it's going to get deflected. If you can imagine water that's falling on the countertop, falling downward, when it hits the counter, it's going to split. So it's going to split towards the North Pole in the northern hemisphere, and it's going to split towards the South Pole in the southern hemisphere. Now what happens is this will eventually lose some of its heat energy and will fall back down as it cools and gets denser. And that happens approximately about 30 degrees north, then also at about 30 degrees south. Okay, so now take a look at these things. When these air currents that are sinking, when they hit the Earth, they're not going to go through the Earth, they're going to split again. So they'll split downward toward the equator, and they'll also move northward toward the pole. Okay, so the same thing, this will continue to happen in the southern hemisphere, but let's just focus in on the northern hemisphere. So in the northern hemisphere, what's going to happen is as your Arctic air cools, it gets very, very dense and is going to sink. The Arctic air is going to sink. It's going to then split in both directions. And then those air currents will continue on their path. But then take a look at what happens at 60 degrees north. We get this convergence of air currents. And those air currents can't go anywhere when they hit each other except for up. This is actually known as the jet stream, where we have these converging air currents, and this rising air gives rise to lots of clouds, and we get cloud formation and lots of fronts. The rising air at the equator will also give us lots of clouds as well. But what we see is this will hit the top of the troposphere, and it'll continue on its way. And what we're doing is we're going to be creating these giant convection currents. So we'll see lots of cloud formation right here. We'll also see lots of cloud formation. I can't really draw it in, but it's going to be cloud formation also at the equator. And the areas at 30 degrees north and 30 degrees south, you have sinking air, and those are usually the areas on the Earth where you get deserts. Think of the Sahara Desert, which is about 30 degrees north. I'm sorry, 30 degrees south in Africa. 30 degrees north, we get the desert Southwest in Arizona, New Mexico, and parts of California. So these are some typical patterns, but we get these giant convection currents. So let's take a look and see the general direction that the air is now moving at the surface. So let's look between 30 and 0. The air is typically flowing from the 30 towards the equator. Okay, just looking at a convection current, that's the general direction. If you go from 30 to 60, the arrow in the convection current is pointing towards the north. So we get a motion that looks like this. And then if you're looking at the convection current between 60 and 90, we're not looking at the currents that are sinking, but we're looking at the surface as it's going from 90 to 60, and it's moving southward like this. So now we have to add to this the Coriolis force. So if you remember that things in the northern hemisphere, they shift off to the right. So as I'm traveling north, to the right is going to be this direction here. If you're traveling to the south, right is going to be to the west. Similarly, between 30 and 0, if you're traveling to the south, if you're traveling to the right, it's going to be to the west. So let's go ahead and finish these arrows for the entire Earth as well. So going to the southern hemisphere, we have the air going in this direction. Okay, it's just going to be a mirror image of what's happening in the northern hemisphere. So it'll be looking like this. It'll be looking like this. Okay, now take into effect that the Coriolis force turns things to the left in the southern hemisphere. To the left is going to shift things off this way. If you're traveling to the south and you have to turn left, you're going to travel this way. Traveling north to the left is going to be this way. So that sets up our global directions of things. And what we can do now is draw in the general direction that the air currents are going to be moving. And they're going to be moving like this in the southern hemisphere, like this, okay, and like this. Okay, in the northern hemisphere, our arrows will look like this. Between 30 and 60, they're going to be moving off to the northeast. And then from 60 to the North Pole, they'll be coming in from the northeast. So now winds are named for the direction in which they come from. So if we can now take a look, you'll notice that this is going to be very similar to this picture that we have down below here. So what we have is we have our northeast trade winds between 0 and 30 north. Those are called the northeast trades because they're coming from the direction of the northeast. In the northern hemisphere between 30 and 60, so here are the northeast trade winds, okay? And then going to your westerlies, yes, they're coming from the southwest, but they're not called the southwesterlies. They're just generally called the westerlies. And then your northeast winds in the poles are not called the northeast trades, but they're called the polar easterlies. So those are the names of the winds. So let's now see how this affects the currents of the water. And these currents form what are called gyres. And gyre means to spin. We have these large ocean circulations. So to simplify this, I'm just going to draw an arrow in one direction. These are my northeast trades. Okay, these are going to be my westerlies and my polar easterlies. Okay, let's do the same thing in the southern hemisphere. These are going to be the southeast trades. Okay, and again, we have the westerlies in this direction. And then we're going to have the, again, the polar easterlies in the southern hemisphere as well. So now let's take a look at what's happening to the water. So these winds at the equator, your trade winds, are going to be pushing your water. And the water is going to be moving off in this direction. And if you think about the Pacific Ocean, let's just title this as being the Pacific Ocean now. So we're looking at the Pacific. And the Pacific Ocean has a continent over here. This is going to be Asia. Here's going to be North America. So these trades are going to be pushing the water toward Asia. Okay, there's Asia. And here is North America. And then we also have South America as well. So there's North America. Here's going to be South America down there. Okay, getting the idea of this hopefully. And what's going to happen is that these currents, these green water currents that I've drawn, are going to hit Asia, and then they're going to diverge. Okay, the water is not going to go through the continent, and this is the major setup for our ocean currents. These will continue, and the ocean currents will continue towards the north, then they'll hit Alaska, and then they'll get diverted down the coast of North America. And this is why we have cold water, because the water is coming from the north. Taking a look at the southern hemisphere, we're going to follow those currents, and we get it looking like this. Now, these same water patterns occur in the Atlantic Ocean. They also occur in the Indian Ocean. So in the northern hemisphere, which direction is this spinning? In the northern hemisphere, we have gyres that spin in the clockwise direction. So down below here, we are having clockwise gyres, clockwise spinning. In the southern hemisphere, you can see that it's going to be counterclockwise. So we have counterclockwise. So that is the setup for how our oceans are spinning in these large gyres. It's due to the wind currents, which is ultimately set up by the curvature of our Earth and the solar radiation and the input that's coming in and the re-radiation of that as heat with rising and sinking airs. That creates our wind patterns, that creates our ocean patterns as well. So if you can go on to the next page, and we need to take a look at upwelling. We talked about these surface currents and surface gyres. We also talked about the density currents. But now what I'd like to do is to focus on these areas right here of upwelling. We've already described what upwelling is. This is when deep water is going to be coming from the surface or from the depths, and it has lots of nutrients in it. And so we'll explain why they have lots of nutrients in them. So we're going to draw a top view of the west coast of North America, and we're going to have over here, here's kind of California, and here's Baja California, okay, Gulf of California. Okay, I'm going to try to draw. Okay, California looks something like this. Okay, then we have Oregon and then Washington. So when we get winds that are coming from the north, okay, we get these north winds. So these north winds often come during the winter and early spring as the storms start to blow through Washington, Oregon, and California. And when we get these north winds, okay, so the wind is traveling in this direction, but now what you need to do is to take into account the Coriolis force and Ekman transport. Ekman transport says that your net transport of water is going to be 45 degrees to the right. So 45 degrees to the right, if you're traveling south, means that water is going to be traveling off in this direction. So we have our north winds, and then we have this Ekman transport. Okay, so I'm just going to draw an arrow here. That's my Ekman transport. Trying to find my window on here. Ekman transport. Okay, so let's take a look at a side view of this whole scenario. Let me go back to the green. The green is going to be the land. So here's our land. And then what I'm going to do is here is the beach. And then we have the continental shelf and the slope and all these other things here. Let's just say this is just off the coast. I'm going to go ahead and draw in some water now. Okay, so what's happening is the wind is coming from the north, and I'm going to give you guys a direction in terms of a side view. So the upwelling in California and the west coast, this is a top view. Looking from the side view, the wind is actually coming right towards your face right now if you're looking directly at a cross section of this. Now think of an arrow. An arrow has a front and it has the head, it also has the tail. The tail of an arrow, if you were to look at it flying away from you, would be the shape of the feathers would form an X. If the arrow were pointing right towards you and the arrow were coming towards your eyes, you would see a point surrounded by a circle. And so in oceanographical terminology, this symbol means that something's coming towards you. So this is the north winds that are coming towards us. Now again, because of the Coriolis force, we're moving off to the southwest with a top view, but from a side view, what's happening is my water is moving off the coast. So if it's moving off the coast, something has to replace it. And when it replaces it, the water has to come from deep down below like this. This is going to be your upwelling. So your upwelling is coming from the deep. Now, creatures that live in the water, we took a look at some of these characteristics. These creatures, like phytoplankton and zooplankton, they live in the water column. And then eventually what happens is they sink and die, or they die and sink. Okay, so they sink and die, or they die and sink. Down on the ocean floor, if you're the abyssal plains, only about 3% of what's at the surface will reach the floor. But this is the coastal region. This is where our continental shelf is. What happens is when it reaches the bottom, we have bacteria and other creatures. They're called decomposers. So we have decomposers. These decomposers, what they do is they eat the biological material. It's their food source, but they're very, very sloppy in their eating. And what they do is they release lots of nutrients into the water. And we'll talk about this in the next chapter when we're talking about microbes. So these decomposers, what they do is they leak nutrients. So as they leak their nutrients, these nutrients are going to rise with the upwelling currents. And what that's going to do is that's going to bring all the nutrients to the surface, and that's going to act as fertilizer for the phytoplankton. That will create what are called blooms and lots of growth. This is why, again, coastal areas have lots of productivity, lots of biological active life, and lots of plant life. And it's because of these upwelling nutrients that are coming from the deep. Okay, so we didn't get a chance to take a look at El Nino. By the way, we are in a La Nina situation, which is the opposite of an El Nino. We can have a normal year, we can have an El Nino year, we can have a La Nina year. During El Ninos, what happens is a lot of the moisture gets shifted toward Southern California. However, during a normal year, it's shifted more towards Northern California. And during a La Nina year, it's even, storm tracks are shifted even further north. So we may have a very wet, possibly a very snowy year if the La Nina conditions continue to pan out. So we're going to be adding lots of things to this graph, and here's some of our terminology. We're going to be drawing in what's called a Pacific high and an Indonesian low. So in the middle of your picture here, if you can draw the high pressure, and the high pressure is going to be right about here, and the Indonesian low is going to be over here. Let's go ahead and put in some land masses as well. Let's go ahead and put in, here's Asia, and here is the Americas. Okay, let's do the El Nino year as well. Here is Asia, and here is the Americas. So we're looking at, again, the Pacific Ocean. So over the Pacific Ocean, we have what's called the Pacific high, and over India and Indonesia, we have what's called the Indonesian low. So a little about weather. High pressure is usually an indication of fair weather. Low pressure systems are going to be indication of rain. This Indonesian low is very, very important, particularly for areas of Indonesia and India, because this brings what are called the monsoon rains. So we have the monsoon rains, and it's due to the low pressure system that's situated over the Indonesia area. That allows the waters to feed lots of the rice crops. So now, also, information about pressure systems. When you have high pressure, air is squeezed and pushed down. Low pressure, you have air that's rising. And in between, what you have is you have winds that are generated that move from the high pressure toward the low pressure system. So we typically get wind that is generated from the high pressure and the low pressure. Let's now go ahead and draw in some of our latitudes. Okay, so we have, here's the equator. Here's the 30 north, the 60 north, and then of course the North Pole. Well, what type of winds do we have in between 0 and 30? We have what are called the trade winds. So the trade winds are blowing in this direction. So we have these trade winds, and what's happening is these trade winds are going to be very strong because they're being reinforced by the Pacific High. So under trade winds, if you can indicate that the trade winds are going to be very strong. Because the trade winds are very strong, let's go ahead and take a look and see what's happening to our water currents. The water is going to be pushed very strongly across the equator. Okay, this is called the equatorial current, and we actually have two of them. We have a north equatorial current. We also have a southern equatorial current in the Pacific Ocean. And what we also have is something that's called the equatorial countercurrent. So if you can draw this, I'm drawing it in the green, you can see that this is going in the opposite direction as the northern equatorial current and the southern equatorial current. So again, this is the equatorial countercurrent. It's going in the opposite direction. What's going to be the strength of the equatorial countercurrent? Well, look at the direction of the winds. The winds from the high pressure to the low pressure and the trade winds are blowing against the equatorial countercurrent. The equatorial countercurrent during these conditions are going to be very, very weak. So the trade winds are strong, the equatorial countercurrent is weak, and your equatorial current is going to be strong. So now let's see what this does in terms of temperature. Well, of course, most of our heat's coming in at the equator, and if you remember the direction of our water currents, let me try to pick a color we haven't used. I'm going to kind of use pinkish color. Okay, so our water currents are in their gyres traveling like this. Okay, clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. So the water from Alaska off of our coast travels towards the equator. As it starts to do so, it starts to pick up some heat. So the water temperature over on our side of the ocean, over here, okay, the water temperature is going to be kind of warm. So we're going to type in, you can put in some warm water right here. Because it's traveling towards the equator, it's picking up more solar radiation. However, it makes an entire path across the Pacific Ocean, and by the time it reaches the other side of the Pacific Ocean, that water has absorbed so much heat, you have very hot water. So you have hot water on the other side of the Pacific. Our side of the Pacific has warm water towards the equator. This is a normal year. But there are some years where the weather patterns shift. And those years are called El Nino years. And again, during El Nino, some of the storms get shifted to the south. They go through Southern California, and they sort of miss our area, and we get low snowfall during El Nino years. So for reasons that scientists still don't really know, what happens is the Indonesian low and the Pacific high switch places. So now what we have is we have this Pacific low, and an Indonesian high. So if you remember, high pressure system is an indication of air being pushed down and squeezed toward the surface. Low pressure has air rising. When you have air rising, you get clouds. So you get lots of storm formation over the Pacific, but where you previously had your monsoon rains, you now have air that's pushing down. Unfortunately, these areas right here, these guys experience drought. And a lot of people in Indonesia starve because they do not get the monsoon rains. Also in Australia, very similar thing happens over here. They experience a drought. When they experience a drought, that's when Australia has lots of their fires. You might have heard about that last year or a couple of years ago with the fires that were in Australia. So let's now follow the wind pattern. Again, air flows from high pressure to low pressure. So because of this, what's that going to do to the trade winds? Look at the previous picture with the red arrow. Okay, these guys are coming from the northeast. Now you have these winds that are pushing against them from the southwest. This creates your trades that are very weak. So I'm drawing it as maybe I'll draw it as a dotted arrow. Okay, we get trade winds that are very weak in this direction. Okay, so down below, if you can put that, the trade winds are now going to be weak. So because our trade winds are weak, our trade winds is what's pushing our water currents. What's going to happen to our water currents? Our water currents in the northern and southern hemisphere are going to get a little bit weaker. So instead of a solid line, maybe draw it as a dashed line. Okay, these are going to get weaker. The north equatorial current and the south equatorial current. Now, take a look at the green line, which is the equatorial countercurrent. It now has the winds that are pushing it from the Indonesian high towards the low. What's going to happen to that current is it's going to get a lot stronger. So the net effect of having this strong equatorial current, let's first of all go ahead and record this down here. My equatorial countercurrent is going to be stronger. The northern and southern equatorial currents, these are going to be weaker. There's this misconception that during an El Nino, that your ocean currents actually go backwards. Well, they don't go backwards. The currents, the equatorial currents weaken, and the counter currents, they get a little bit stronger. So the net effect of this is, let's now follow our path of water. So we're going to follow this. So we've just had water that's come from the equator. It's going to lose some heat. Now it's going to enter into the equatorial currents. It's going to travel across the equator, and it's going to have a second passing towards, back towards the Americas. So we actually get 2 heatings of water, or double the heat, approximately. So that's the net effect that we get from this. Let me go and do this in green. Okay, the net effect is we have a second trip. And that second trip is across the equator. So we get a second trip across the equator. What's that going to do to the water temperatures? Well, instead of the water temperatures being very hot towards Indonesia, the water temperatures over here tend to be warm. So you have warm water. And over here, off of our coast, North America and South America, we have hot water. So because we've increased the temperature of the water, we also make evaporation a lot easier. So the net result of having an El Nino situation is we're going to increase the water temperatures. So I'm going to put this up to the right here. We increase the temperature of the water, and when we do that, that's going to increase evaporation. And when you increase evaporation, you're then going to increase the amount of rainfall. And that's what happens during El Niños. We get lots of rain towards the equator on our side of the Pacific. So we are the West Coast. However, we are the Eastern Pacific. Asia is actually the Western Pacific. So in the Eastern Pacific, we get an increased amount of rainfall due to the increased evaporation because the temperatures are warmer, because the water is having a double heating. Okay, that's going to be it for this part of the lecture. And then what we're going to do is I'm going to have continuation on our PowerPoint.